Hello, time for a deep learning demo. So in this demo, I'm going to show how to use Keras to do multi-class classification. This will be based on a tutorial provided by TensorFlow to use Keras. And in this case, I'm going to use multi-class classification instead of binary classification, which the tutorial has that's part of the TensorFlow documentation. The way we're going to do it is we're going to use BERT to classify text and then add a layer so that that text can be classified according to the way that we'd like to classify it. Additionally, I'm going to show how to use Horovod to run the learning that's required to train the Keras model over a Spark cluster so that you can do distributed deep learning. So this is what I'm going to demonstrate. I'm going to demonstrate how to adapt TensorFlow BERT from a binary classification to multi-class classification. I'm going to apply the classification model to a problem where you classify text. In this case, it's similar to another project that's already been completed where the researchers used a BERT variation to classify software text requirements into different categories of non-functional requirements. I'm going to show how to run it in Python and also in PySpark using Horovod. And it's going to run on Google's cloud. So this is how it works. This is from this paper by Tobias Hay and colleagues. And they used NoRBERT, which it's a variation on BERT. The details don't matter, but it's a BERT classifier where in comes some text, and this will be a requirement, a software requirement that you might have from a software document, requirements document, and this can parse that software requirements document, and then out of BERT comes some information about the natural language, and then they have added onto it a layer to the Keras model. Well, they use PyTorch to their neural net model. They add a layer that allows them to classify the resulting output from BERT so that they can output and classify requirements. And skipping over the first category, they have all these other categories of non-functional requirements, also known as NFRs, and you can read about the paper here. And most of them have a number of examples. There's not a ton of examples, but there's a fair number. In this case, there's only one example, and in this paper, they just drop that and they don't classify it, so I dropped it as well. Although you can run it, and there's a way to duplicate the row in order to have more instances, and then you can run the classifier, but that's in the code. I'm not really going to talk about it much. So here's the idea. BERT is a large language model, and this is pretty exciting these days because people talk about Chat GPT as being a large language model, and that's very popular when I'm recording this. So BERT's a little bit older. It's from 2018, and it's very clever. It takes a sentence, divided up into tokens, and then comes up with a number for each one of these words called an embedding. And it was trained on lots of data to come up with the proper embedding. And you can find out all sorts of information about this, which I can't go over here. But it's a very clever system to look at text and have some representation of the text that considers both the words and also the sequence of words in the sentence itself. So consider sequencing and the words. So once you have this BERT pre-trained model, then you can add your own layer to this model, sometimes called transfer learning, so that you can use BERT and then apply your model in order to use the power of BERT to classify the text that you want to classify. So here are some of the scores, and I'm going to try to do my best to do as good or better than this. NoRBERT, which classified precision, recall, and F1 measure for a particular data set of non-functional requirements. So the goal here is to use Keras instead of PyTorch. So if you look at the GitHub repository for the code that Hay and his colleagues developed some time ago, they use PyTorch. And if you're new to developing these deep learning models, it can be a little bit intimidating or complicated or time consuming. So for most cases, I think it's fine and maybe better to use Keras. There's lots of information about how to use Keras, and I'm going to show you one demo here that takes the project they have here in PyTorch, but just applies it, the same ideas to Keras. So let's see what we can come up with. So the question is, can I implement that project, that classifier, for the same data set, perhaps with fewer lines of code, and come up with the same or better results? That's the, just something I wanted to do as a project, thought it would be fun. That's the kind of fun I have. So in order to understand TensorFlow, I recommend, if you don't know about it, then you look at Aladdin Pearson's greatest ever tutorial on it. So go to his website. It's a great video. It talks about how to do TensorFlow in Python. All right, so that's a good start. You don't need it to do my demo, but if you want to follow up, then I recommend you do follow up. He also goes through Keras, if I recall, in the demo. He recommends a number of other sites if you want to know even more about the deep learning and these neural networks. And one I really like a lot that he recommended is this 3 Blue 1 Brown website that introduces people to the concepts, not the coding, just the concepts of deep learning or neural networks. It's a great site. I can't recommend it enough. So about the time of this recording, we have a number of issues that have come out about Chat GPT. So I just want to take a brief aside and say there's some Google engineer, or at least there's one that says, their AI has come to life, and it's related to this generative AI is the phrase. And I recommend maybe you can read the article, and then you can also look at something like Chat GPT 3, which is the current one at the time of this recording, or mostly the current, and BERT. So you can compare that. We're going to use a version of BERT today. And it's an interesting discussion. If you're a technology person, I think that you should be aware of this issue. So I want to take just a brief moment to demystify some of the technology. I don't have time to go through it all, but I'm trying to provide some references. So one thing I think is really cool to look at is, hey, you heard about Chat GPT, go build your own Chat GPT. And in the process, you really understand quite a bit more about understanding text, how the computer does, as well as the generative portion for generative AI. And I believe I have a previous video that did a little bit of this and did some generative AI. I didn't call it that at the time, but you can look at it. Summary, they call it, generating a summary from reading a document. But it's worthwhile looking at this video, I think, if you're really interested in the details. But again, you don't have to know it for today. But just a little bit of a summary from some of the references I just pointed out, that these neural networks, or also known as deep learning, will take an image or text as input. In this case, it's an image. You can think about the input being a vector or a list of 784 items. And we'll take this image and divide it up into segments or little bits of data, such that there's those 784 pieces of data. And we'll feed this into our neural network. That's what this is here, this deep learning model. And the first 784 bits of data are connected to our input layer. And then if there's, say, a little bit of white here on this input node or neuron, then it's going to light up and pass a little bit of information meaning a number, maybe a 1 or a 0, or some number between 1 and 0, depending on how it matches. It'll pass it on to the next layer. This is an internal layer, and then that'll pass on to the next layer. The idea of these middle layers, it will take, say, a couple or a few of these neurons from the input layer, and together say, oh, these three things together represent a feature. So then it says, oh, I recognize part of the number 9, and I'm going to pass it on. And then the next layer looks at the previous layers and so forth. And in the end, you hope that this sort of pinball machine, when all these layers go through and light up things, they recognize that, yeah, this is a 9. So the last layer, the output layer, is your classification layer. And it's saying, I recognize, classify this input as a 9. So that's the idea. The last layer classifies the signal that's transmitted through the layers. And this is relatively small. It's pretty good size, 784 inputs, and then 2 intermediate layers, and then the last classification layer. So that's a little bit how it works conceptually. And then you might wonder how it gets trained. Well, you pass it in a bunch of training samples like this 3, and your training labeled data says, here's the output vector, this is what it should look like, and by the way, it should light up 3 and only 3. But your system, your model, it lights up 3 and a bunch of other junk here. So it's not exactly perfect, as they say in the video. Well, this is utter trash, it's wrong. So then you can look at the difference between these two lists or vectors, these two vectors, and compare them. And if there's quite a bit of difference, then it's bad, and it's very close, then it's good. So there's a cost function here, which you can look at squaring the differences of these two vectors. And what you're trying to do then, of course, is minimize the difference here. It's sort of like regression. It's a variation on regression, if you're familiar with least squares. Anyway, so the idea here is we're trying to minimize the differences between these two vectors. And one way we can do it is this process they call gradient descent. And we have all of these neurons, and they have weights. And the weights get modified as they train the data set. And which ones do you modify? Well, there's this gradient on this cost function that gives you some idea of, out of all these parameters, I'm going to call now all the weights associated with these neurons, I'm going to call them parameters. Out of all these parameters, which ones do you change? And today we have, hundreds of thousands, millions, and billions of parameters as you work your way up into the, having more money to generate larger parameters for larger models. In any case, the idea is to minimize this cost function, and it's explained in this conceptually in this video where I've taken a few screen image. The idea is you modify some of these parameters so that in the end it gets closer and closer to the correct solution. The cost function is smaller and smaller so that it equals the best and correct solution. That's the idea. So if you're familiar with numerical analysis, the idea is that you have this, or calculus, you have this image of your function, and you can think about it sort of a ball. You want to roll the ball down to the lowest part of this function to find the minimum. And if the function is properly formed, then there'll be a single minimum, and people come up with clever ways to represent it. So there is a single minimum, and that's the idea, is that you're going to adjust the parameters in this giant neural network such that as you change them progressively, they get closer and closer to the correct solution. If you want to know further about it, then you can look at calculus, which calculates a derivative, and that derivative tells you which way to go, which way to modify the parameters in your cost function. And if it's been a while since you've done calculus like it was for me, then you can go to, say, Khan Academy and look up their AP calculus and look at the chain rule. This is partial derivatives here, but it doesn't matter. Same for, single variable calculus. And the chain rule helps you figure out how to modify your functions so that we can approach the minimum by changing some of the parameters. You don't have to know all of this. The beauty is the API provided by Spark or by Python, they provide these, but you'll want to look into the optimizers and understand some of this in order to pick the correct optimizer and the one that's going to move quickly towards the minimum, the cost function being smallest, and then the best solution. This is a little bit about how this all works, and if you want to know more, once again, look at this website, Deep Learning AI, and I've got a link to it, and you can see in the information on this video. It explains all this in great detail. It's a wonderful course. Okay, so in summary, BERT is a large language model. It implements deep learning, also known as a neural network. It has an input vector, and instead of parts of a image for, say, the number 3, each one of these inputs is going to be a word that's going to be tokenized. Our sentence is going to be a set of words. And we're going to connect our sentence to this neural net. That's this first input layer. And then the neural network is very clever because it's going to use this back propagation to iteratively try to minimize the cost function and thus come up with a model that properly characterizes, properly selects, classifies the input according to your labeled correct description of the data. Okay, so at least in my opinion, this little bit of calculus that is a fancy regression is not a sentient being. That's my opinion. All right, so on to using it. So back to the paper. I want to duplicate this paper, but I don't want to use PyTorch because it's so complicated. Well, not so, but it's more complicated than it needs to be. So we're going to, they took BERT, added a layer to it for classifying text and output the classification, and here's their output. Can I do it? Let's see. All right, so start with the demo from TensorFlow tutorials, and they've got a great demo there. If you can look through it, it explains great detail about how to run binary classification. And this is roughly what it looks like to build a model. There's an input layer. There's a pre-processing layer that's necessary to take text. And then BERT encodes that. And then we can add some of our own layers. And here's how it is in Python, just plain old Python. There's an input layer that's going to take our text. So it's going to read whatever text we give it. Then there's a pre-processing layer that's required for BERT. And the output of the input layer, it's called text input, it gets passed to this pre-processing layer. Okay, up next, the output of that pre-processing layer goes to our BERT encoder, which is this, can be quite a large pre-trained model that was created by Google that reads a bunch of text and gives you some useful information for classifying that text. Then, once we have that, we can send that output onto some of our layers, and this is sort of the part that we add on. And this is from the demo in TensorFlow. They use a dropout rate of 0.1 or 1%, and then they end up classifying the result. And here's a key element here to look at. That is, how many classes should we classify the result? And it's just 0, 1, so it's binary output here. So that's the example from the TensorFlow example in the tutorials. So we want to take that and then do multi-class classification. And this over here is just to give you a reminder of what we're working with here. Here's our input layer, and that's this layer here. And we have some intermediate layers, and that's some of the BERT. Essentially, this BERT layer is going to be sort of in this middle. And then we're adding somewhere towards the end a couple layers here to do dropout and do classification. So that's the idea. Right, so for the problem I have, duplicating the work of Hay and colleagues, instead of having only one binary classification output, we have multi-class. So this is the difference. So this will allow us to do multi-class classification. And then in addition, we want to reduce overfitting. It's just something to consider. I don't do, this is a little bit different than the original. So we add in batch normalization, also known as batch norm, which is going to reduce overfitting so that when our model sees data that it hasn't seen before, hopefully it'll still perform reasonably well. And also we're going to do regularization. This is L2 regularization, which is essentially the same thing that you'll see if you're familiar with linear regression. People often use L2 regularization. So a little bit about these extra layers that we've added. We have dropout. It randomly mutes or reduces the impact of some of the neurons. You could specify the percentage. I think 0.1 was the value used in the example. You can have batch normalization, which converts the values in the network to a standard scaling or standard scale. Mean is 0 and standard deviation of 1. And this, through various ways, can reduce overfitting. And then we have regularization, which often helps the case where you have some outliers. So there's some links here if you want to know more, but these are some of the additions that I've added to this work that I basically took from Hay. I took his model, converted it from PyTorch to Keras, but I wanted to add some things that are commonly done today because it's pretty easy to do dropout, normalization, regularization. All right, so the results, here's his paper results, and you can have larger and smaller models. Here's the large model of BERT. Talked about the models, and he got 94 for F1 measure. And this, well, it turned out to be perfect, but it's not always going to be that way. It's a small data set. So in any case, we're pretty close, at least as good as the original, it seems. So if you want to see how all of this works, the code is always on data demo. Here's a TensorFlow that you can see from the providers of TensorFlow. They have this binary classification, BERT, which is what I based my code on, and then the original Hayes GitHub repository. All right, so that's what we're going to do. I'm going to show it here in a moment. But first, I want to go on to something new, and that is how to do this, not just the standard way that a lot of people do using Python, but today we're going to use, in the future, we're going to use things like Chat GPT. Our models need to be very large, and so running on a single node computer for training is not going to work. So people like Uber use Horovod, and you can see a great speed up by running your models over a cluster when you train them. And that's the idea we're going to do here. This is relatively new technology, and sometimes it works okay and sometimes it doesn't. For me, your mileage may vary, but generally the at least conceptually the idea is that you have multiple nodes in your cluster, your computer cluster, and the model is training on each one of those nodes, and they're computing the parameters. They call them here gradients, so it's part of the loss function. We called it the cost function. And the idea is to take those parameters and average them out and get your final model. So we can train multiple models, portions of the model using different variables, different parameter values, and then combine them. So that's the idea. So originally, the original version of Horovod, this is what they did. They constructed a Spark context, and then they initialized Horovod, and then they used this Spark run to train the model. And since that initial, I just show it here because you'll see this in some of the tutorials, but they've changed it a little bit, and now here's how it works. And maybe by the time you see this video, they'll change it again. But here's the idea. this is a Horovod namespace, and they have this function for Keras estimator. This one reason, again, to use Keras, it's not only easy to use within Python, but it's used by Horovod. You can also use other things in Horovod, but they have a nice interface with Keras. And then you just give it your model and your optimizer, and basically then tell it to fit. And then it runs, and then you're done. Okay, so let's see if it runs for me. So let's go to the demo. So let's hope the demo works today. Okay, here I am in the demo. I just want to point out once again that here's the paper I based the classifier on. It's worth reading the paper. And here's his GitHub repository for this. It does a lot more than I'm describing in this demo, so if you're interested, please look at it. Here's my Colab notebook. You can see I have a little bit outlined here on the left, and it summarizes what we just talked about. I'm going to use classification of software requirements using deep learning. This is an example using originally Python and later on PySpark. It's mentioned here, it does basically the same thing as the original model by Hay. It adds a little bit that I mentioned, batch normalization, L2 regularization. It also adds some class weights to address imbalanced data. So there's some links here to look at, and then let's go through a little bit of it. I just ran it, so just hopefully I don't have to rerun it again. But the first part is just to install some of the libraries. So here's installing, updating pip, installing TensorFlow. And there were some issues with versions of NumPy. Maybe by the time that you run it, this won't be an issue, but I had to try to, to get all the versions to match. So this was important in this case. Print out the versions. I have TensorFlow, and then some other imports as well. Well, this is just loading the libraries and then the imports. The data I just got directly from Hay's website. We'll just download it here and load it into a pandas data frame and print it out. And so you can see some of these things here from the promised data set. The system shall refresh the display every 60 seconds. And then the kind of requirement is, if it's an NFR non-functional requirement, that'll be 1. If it's functional, it'll be 1 here. Today I'm just looking at the non-functional requirements, and then here's the tags or classifications of them in the trained data set. So this is the data set we're given. Just do a little processing to print out information about the different kinds of classes and how many classes. There are 11 here. A little bit of, graphing is always helpful when you're going to get ready to do some data analysis, and it turns out this one class only has one member, so it's probably best to drop it or replicate it. There's a little bit of code here, so you can replicate it, but I did as the paper did, and I just dropped it. So in the final data set here, you can see now I've only got 10 classes. Okay, next up, take those text labels of the classes and convert them to numbers. So I just use the label encoder from sklearn, and then just printed out the data here just to see that it seems to be working. Next up, I use the class weight function from sklearn to come up with some class weights to address the imbalance of the data. And just a note here about using different kinds of optimizers. Some cases, the class weights don't work well with the optimizer. So just a note, I'm going to use the atom, or a variation on atom optimizer, and so it doesn't affect that. So atom is good with class weights. All right, next up, just grab this code again as a basis from the TensorFlow tutorial, and you can select one of the many BERT models. And just to note that some of them are bigger than others, like 128 is going to be smaller than 768, right? So some models are large and some are small. And later on, you'll see that I use a smaller model because because I didn't have the memory in this free version of Colab. Okay, so going through, if you look at the code here, it pulls off the model, downloads it, and then puts it in these encoder and preprocessor variables. Okay, so I use that here. You can see the preprocessor. So using that, then I check to see if it's going to work, and this is based once again on the TensorFlow tutorial. So I followed what they did, and you can see that we can have a bit of input. This is one instance, one training piece of data, the text, and we can see that it gets processed by BERT, pre-processed by BERT properly, and same with the output of BERT itself. All right, now we're going to go on to specifying a model that's like the original model in NoRBERT. And we have just a slight variation on what we did as to what they did. So here's the model. Same, I think, as in my slide deck, is that you have input as text, you have a BERT required preprocessor, then the BERT encoder. And then that takes us down to about here, where we can have a dropout of 0.1, then some normalization, then regularization, and then our classifier according to the number of classes, which should be 10 above, hopefully. And then we'll have our multi-class classification. So the trick, if you're going to go from binary to multi-class, is this: you have to have a layer where the number of classes is more than one. That's the key element to it. It's really not much more to it. And that's why I think this in particular is pretty easy to work with as opposed to TensorFlow, which is fine. It just, I prefer it when, if you can use something simpler, I like to use something simpler. All right, so once we have our model, which this returns the model that we built, and it's called model in the variable, then we can go ahead and print out a summary of it and plot it. And here's a bit of a summary of the model. It's convenient to do this sort of thing to say, oh yeah, it looks like that's what I intended to write, so you didn't make a mistake. All right, next up, we'll check the model and see if it does classification. So we give it a sentence here, and it classifies it as LF and has a weight, sort of a probability of that being the proper classification. And I have a little code here in case I want to save the model, which I didn't run for this example. Next up, I have a few training parameters, which I put in a simple dictionary, like the number of classes, the batch size, and some other things, learning rate, and so forth. The details of which I'm not going to go over, but just giving the idea of how this overall process works. So next up, some model metrics, which I grabbed from a Towards Data Science article, which is pretty nice, about balanced recall as opposed to just recall and so forth. So these work well for doing it. Python did not work well with Horovod, but here's some metrics. So I'm going to output these metrics for accuracy, recall, precision, and F1 score. I also have run a number of folds and in-fold cross-validation, and I just have a simple function here to print out the results of that, some scores here, some of the metrics. And in addition to the metrics I've specified, I also use the sklearn classification report, which is helpful. And then I grabbed some code from I think Towards Data Science to graph it all. So here's a function to graph this as it goes along. And the next step, here's the function I use to do the fitting, the cross-validation fitting. And give it my Keras model and my X and Y's, number of classes, the number of epochs and batch size, the number of folds, and the last little parameter here, which is sort of off the screen, is whether to graph it or not. And if you're going to do more than one fold, which I do in this example, then it goes through this little bit of code. It makes sure it does stratified folds, to make sure that each fold has the proper 11, I think, or 10 classes that we have. That's what that's about. We can also process without folds. So there's my function to do the cross-validation fitting. And then finally just print out the information, the summary. Right. In order to help this, I just put all my parameters about this into my dictionary. Maybe I did that above too. And I have an optimizer. And so there's a number of steps here specified how many steps I want to go through and how many epochs. But the key element here is going to use Atom W as our optimizer, and we're going to use a cosine decay. So initially our steps as we do our optimization are larger, and as we get closer and closer to the final solution, our steps are going to be smaller. So you don't have to use this, but it seems to, it's going to be faster if you use some sort of scheduled decay typically. All right, so once I have my model defined above, I'm going to compile the whole thing with my optimizer, my loss function, and my metrics, which I defined above, which are just a list of metrics. My loss function is this categorical cross entropy, which I think is the default. All right, now I run it. So I'm going to go ahead and run my model, cross-validate. I pass in my model, my x's, my y's, the number of classes, the epochs, the batch size, and so forth. I think I ran 4 folds here. Yeah, and I wanted to graph it. You don't have to graph it, but I like to graph it so I can see what's going on. So we scroll through, oops, we can see the first fold, and then the processing of the epochs. And you can see, over time, of course, the idea is the loss, the accuracy, the function gets smaller, the error gets smaller and smaller, and the accuracy and all the other measures of how good the model is increase. So recall and so forth should increase. And we do this for 4 folds. So here's the second fold, the third fold, the fourth fold. It's a little bit crazy in some cases, but in the end, take an average of all those and also pull out the best model. So the average was, I think balanced F1 is probably the best one to look at, is about 79. But when you pull out the best model out of all that processing, then you get an F1 score of 1. So there's the model. It seems to be pretty good. At least as good as the original in the other paper. So the goal here was to use Keras. And I mean, I have all these other functions are here. It seems like a lot of code, but it's just to print out some metrics. The key bit is this. And I think if you look at this and compare with the original, you'll see that the Keras modeling here is a little bit more compact and perhaps easier to read. Okay, so we're done. So what did we do? We took the TensorFlow example about using BERT to classify binary classification. We adapted it for multi-class classification. We compared it with an existing project that did classify requirements text, and it seemed to perform as well. And I think if you compare the code, it's a little bit smaller, simpler, and easy to read. We ran it in Python, which is sort of the standard. Most of your examples are there. But also we ran it in PySpark, and in order to use that in PySpark, which allows you to do your training over a distributed cluster, then we used Horovod, which seems to be a very popular framework for this purpose. All right, so that's all we got. I hope it works for you. Good luck.